Hi, my name is Muhammad Hamizan, and today I'll be giving you an overview of our integrated design project. Here is all the group members, Iqbal, me, Erica, and Aina. So we're entering our first chapter, the principles of chemical engineering. This course is an obligatory component for all chemical engineering students. It will cover introduction to chemical industry, chemical engineering calculations, and will prepare us for process design and evaluation. After completion, we are expected to analyze conservation equations, interpret process data, and perform material and energy balance. So here is our process flow diagram for the production of isopropyl alcohol. We have two feeds, hydrogen and acetone. Both of these feeds will be pressurized using a compressor and a pump respectively. After the hydrogen compressed feed is cooled down using a cooler, these two feeds will be mixed into a mixed feed using a mixer. This mixed feed will then be fed to a hydrogenation reactor, which will make them undergo a reaction to produce isopropyl alcohol. This reacted mix is then cooled by a second cooler, and by then, the two mixtures will then be separated into two outlets, a gas outlet and a liquid outlet.
Next up, for Chapter 2, we'll dive deeper into the principles of chemical engineering. There are two parts in this section, which are mass balance and energy balance, were being used in producing isopropyl alcohol. Before that, let's get to know some basics about mass balance. It is the law of conservation of mass states that for any process unit, mass can neither be created or destroyed, but it can change from one phase to another phase or converted into other forms through reaction processes. The law concludes that total mass input equals to total mass output. So we perform mass balance to assess production efficiency, manage resources effectively, and analyze economy. By tracking material flow, we can optimize processes and identify cost-saving opportunities. In this section, we use mass balance to determine flow rates and coupling fractions in the hydrogenation reactor and the distillation column. The assumptions will be made, and the objective was to understand mass flow within the unit operation. So we divide the mass balance into reactive and non-reactive system. For the hydrogenation reactor, we assuming that 400 kmol per hour of molar flow rate input, and we calculated molar flow rates for each component based on stoichiometry and conversion efficiency. So molar fractions were calculated for each component in the inlet and outlet streams, in understanding material distribution. To calculate molar flow rate for each component, the molar flow rate divided by the total molar flow rate. Finally, we converted the molar flow rates to the mass flow rates using the molecular weight, and calculated molar fractions by dividing mass flow rates to the total mass flow rate. So based on the tabulated data, we can see that molar flow rate and also mass flow rate for isopropyl alcohol is larger compared to acetone and hydrogen gas. It is our goal to achieve high value for the isopropyl alcohol. Next, we'll be calculating mass balance for non-reactive system, which is the separation of isopropyl alcohol. So assumptions made are as given. By applying the calculation of total flow rate in equals to total flow rate out, we can obtain the molar flow rate in the top and bottom stream. So, to summarize, mole fraction E of isopropyl alcohol in the bottom stream are high in value compared to acetone and hydrogen. However, in the top stream, hydrogen gas has higher mole fraction compared to the acetone and isopropyl alcohol. Same goes to the mass and mole flow rate tabulated data, which are our goal to achieve high value of isopropyl alcohol.
So I will be covering for the overall view of our energy balance. So for this second part, energy balance was used to determine the enthalpy for each component of the inlet and outlet streams, and thus determine the change of enthalpy in the process units. The selected reactive and non-reactive units are the same as the previous mass balance, and all the assumptions and references given are stated. The main objective of this part is to give a better perspective on the energy change within the unit operation. So we have the energy balance for the reactive units. So as you can see here, besides from the assumption and references from the previous mass balance for reactive units, we also assume that all gases are treated as either gases, all liquids are incompressible, and we set a reference state for 25 degrees Celsius and 1 atm for all components. As you can see, the temperature rises from 25.7 degrees Celsius to 224.7 degrees Celsius, and the pressure does not increase at all at the same 21.7 bar. So as you can see here, the component, we have listed all the components, the mole flow, the enthalpy change for each of the inlet and outlet stream. And at the end of our calculation, we found that the total change of enthalpy for the reactive unit is negative 16,722.56 kilojoule per second. Moving on to the energy balance for the non-reactive unit, the separator. As you can see, the temperature for the inlet and the top outlet streams are the same. The pressure are also the same, but the temperature for the outlet stream for the bottom product, that is the liquid product, is 25 degrees Celsius. So as before, all the assumptions and references are the same as the before for reactive unit. And this table shows all the inlets and outlet streams, mole flow, and enthalpy. So after calculation, we found that the enthalpy change is negative 779.655 kilojoule per second for non-reactive units.
Assalamualaikum, hi, my name is Iqbal. Now I will continue with Chemical Engineering Fluid Mechanics part. Introduction. Chemical Engineering Fluid Mechanics is 3 credit hours course program of Bachelor of Chemical Engineering in TP. The fluid mechanics course focuses on distinguishing between gases and liquid, evaluating unit fluid characteristics such as viscosity and density. Upon completion, students will be able to apply concept of fluid static and dynamics, analyze internal and external fluid issues, understand fluid application in chemical engineering unit operations. Next, I will continue with our fluid mechanics task. This is our designated pipeline layout, and these are all this is a table that shows all the connection of the stream. Next, I will continue with pressure drop calculations. For pipe 2, these are all the assumptions and references. Firstly, 3-inch cradle 40 stainless steel pipe with inside diameter 3.068 inch. Length of the pipe is 4 meter. Elevation of the pipe 2 meter. Pump bore equal to 21.76 joule per kilogram. 290 degrees steady elbow, 1 chair valve, no turbine. Steady flow rate with m dot equal to 23,200 kg per hour. Density of acetone 784 kg per meter cube. Viscosity equal to 0.306 times 10 to the power 3. Next, let's jump to the calculation of pressure drop for each pipe. There are 6 steps to obtain the pressure drop for each pipe. Firstly, converting mass flow rate from kg per hour to kg per second. After that, determining V by using this formula, m dot equal to rho UA. The third step is determining Reynolds number by using this formula to determine whether the fluid in the pipe is turbulent or laminar flow. After that, we can calculate friction factor by using the formula or referring to the model diagram. The fifth step is calculating the total friction loss by including all the losses such as fitting, KC and KE. And the last step is calculating the pressure drop by using the Bernoulli equations. Plug in all the informations and cancel all the terms that can cancel out, rearrange back the equations and plug in the value. Now we can get the pressure drops for pipe 2. All the steps are the same for other pipes and we just need to repeat it. And lastly, this is the summary table for pressure drop. That's all from me, thank you.
So I'm going to explain the transportation strategy of isopropyl alcohol from distillation column to the storage tank. From the sketch, we can observe that the storage tank is located at higher elevation than the distillation column, connected by a 4-inch schedule Berthiez stainless steel pipe. We use stainless steel pipe as stainless steel is highly resistant to corrosion and oxidation, chemically inert, and also has high strength and durability. We chose a larger diameter pipe to reduce pressure drop and enhance energy efficiency. The pipe is also insulated to minimize heat loss or gain. As for the pipe fittings, two 90-degree standard elbows and a globe valve are installed to regulate flow and pressure within the pipeline. A centrifugal pump is installed to pump the isopropyl alcohol against gravity to the top of the tank. Next, let's have a look at the specifications of the storage tank. Firstly, the material used is 304 stainless steel, which has higher corrosion and oxidation resistance as well as high durability. To be able to contain 100,000 gallons of isopropyl alcohol produced, we set the height of the tank to be at 12 meters Based on the cylindrical volume formula B equals to pi r square h, we can estimate the diameter of the storage tank to be 7 meters. The thickness of the tank wall is set to be 8 millimeters to withstand internal pressure. Lastly, the tank is located above ground to ensure it is well ventilated. Next, let's do some calculations to estimate the pump power needed to pump the isopropyl alcohol. By having all the specifications of the pipe, we can start doing our calculations. Firstly, we use Moeller flow rate to find out the velocity of the fluid flow to determine the Reynolds number. Because the Reynolds number is more than 4000, we can assume the fluid flow to be turbulent. The friction factor is then calculated by using the formula for turbulent flow. Next, total friction loss from the pipe fittings, contraction and enlargement is calculated. Then by substituting total friction loss F into the Bernoulli's equation, we found out that the pump work is around 110 joules per kilogram. Lastly, knowing the efficiency of the pump is 95%, we can calculate the actual pump power, which turns out to be around 764 watts.
Now we are on our last agenda, which is the conclusions. In summary, the integrated design project has significantly improved students' comprehension of the chemical industry, fundamental chemical engineering calculations, critical thinking, and problem-solving abilities. Additionally, integrating fluid mechanics into the project has helped students tackle complex issues and connect principles of chemical engineering to develop the foundational skills necessary for their engineering courses. I believe that is all from us. Thank you.